Good afternoon, everybody. Today, it is a pleasure to welcome you to the new Joint Astronomical Colloquium of this week, and a real honor to introduce Joao Alves. Joao is a worldwide expert in star formation, the interstellar medium, in particular recently the use of Gaia to shed new light on all of these things. And to briefly introduce the speaker today, Joao got his PhD in 1999 from both University of Lisbon and the Harvard CFA, then moved to ESO as an ESO fellow, where he then subsequently became ESO staff. In 2006, Joao became director of the Calar Alto Observatory, and since 2010, Joao is a full professor at the University of Vienna. And last year in particular, he spent a sabbatical at the CFA and Harvard as a Radcliffe Fellow. And I think you will be talking to quite a bit of the work you did there during that year today.
Will, yeah.
Yes, excellent. So I look forward to that. So let's give our speaker a very warm welcome, and then the floor is yours.
Thank you very much. So it is a great pleasure to be here in Heidelberg. I will talk to you mostly about the distribution of gas in a local neighborhood. This is work done with my group in Vienna, and this is Stefan Meingast, a postdoc, Josefa Groschedi, a student, and Verena Funkrantz, a master's student that's moving to a PhD here in Heidelberg. And then, very crucially, Katrin Zucker is a student at Harvard, in Elisa Goodman's group, Josh Spiegel, Tom Robitaille, Doug Stickbeiner, Ed Schlafly, and Greg Green, which I didn't know is not in Kavli, is now at the Max Planck here. Great move. Okay, so although I work mostly on star formation, understanding how stars form and what are the conditions for stellar birth, this talk is mostly about trying to figure out how we go from 2D in the sky to 3D, and can we use Gaia to do that? Obviously the answer is yes, and I have a couple of results. I would say a first one where I will prove to you, studying a cloud called Orion A, that we can do this. We can measure the 3D structure of a molecular cloud. This is fundamental for a lot of reasons. More than that, and this is a program we're trying to develop in Vienna via ESO public survey called Visions. We're trying to measure the motion of the ISM in 3D. So we know motions of stars fairly well now with Gaia. With gas, it's much, much harder. We know very well the radial velocity. It's very hard to measure the proper motion of the gas. And then finally, something that came from my time at Radcliffe last year, which was an investigation on the distribution of the local clouds and trying to figure out what's in front of what in this very massive picture of the plane of the galaxy. So let me show you then what I normally do. This is Ophiuchus, which was this region over here. This is Galactic Center here, and then there's Ophiuchus, and there's famous cosine associations full of massive stars. 10 to the 4 stars were formed in the last 15 million years. And if you look at where stars are forming right now, and it's the very, very center of this picture, this is 1688. And what you're seeing here is a dust emission from Planck, and it's color-coded with temperature, roughly. So red means something like 10K, blue means something like 30K. What you're missing from this picture, and this is where now Gaia starts playing a fundamental role in trying to bring together the radio ISM community on board, is the stars. And in fact, now if you put the stars into this picture, all the hot spots, and in fact I would argue all the structure you're seeing here, is actually forced by the feedback of stars like these ones. All of the stars here are ionizing sources, B3 and above. The supernova took place somewhere here, because we know this guy's proper motion, this Zeta O, very famous star, came from here, and we think it was a binary that exploded and ejected this O star. And what you have is the ISM reacting to all these forces that are impinging on it. So I will now go on just to show you why we should care about clouds. We'll focus on there, and using vision data, and that's the closest embedded cluster to Earth, the cluster stellar nursery. And what you're seeing here is there's a shock front here. This is for another talk, but the highly structured distribution of gas. In fact, what you're seeing here are cores. You can find disks here. And this is the environment, the typical environment where probably our sun was formed. And this is interesting for a lot of reasons, one of them being the enrichment of, for example, radionuclides. We know that aluminum-26 was, our solar system was enriched at the very beginning. Well, this is probably how it happened. You have supernovas and winds coming from in this case, the upper skull region. This is a cluster formed 10 million years before the stars forming right there. And the transfer is done here, where if you look in the optical, you wouldn't see a thing. Now we're looking at 2 microns, you get to see through the cloud, but you cannot really see through the very dense cores like these ones here. But you do see the background. It tells you that you are probing the stellar background on the end. But the idea, of course, is that you have an ISM that's highly reactive to, in this case, feedback. Here's a gallery of cores that eventually become embedded objects and very embedded objects with, in this case, disks, and eventually more evolved. This is all in Ophiuchus. Now, if you go down from Ophiuchus, you get the Pipe Nebula, and I'm just going to quickly go through what I normally do before I go to how these all relate in the sky. The Pipe Nebula is great because it's further away from the big action up there. Ophiuchus is somewhere there now. There's only stars forming at the edge here. And what we've been developing for a long time is a way to measure column density, high precision measurements of column density through the clouds. And we do that with near infrared when you measure the color of the stars on the other side of the cloud. And we do this at 2 microns because the clouds become transparent. When you do that, you have millions of lines of sight, like quasars for people who study the intergalactic medium. We have millions of lines of sight towards the cloud where you can then construct an accurate distribution of mass inside this cloud. So if you do that, you get that. And then you start to realize, well, there's something interesting about this scale. And these are, of course, the dense cores. These are the reservoirs that eventually will collapse on your giant molecular cloud. Only these little, tiny little things, we call it dense cores, will collapse and form solar systems like our own. Here's one of them. And by studying them in the infrared, just like the method we use, basically, this is the optical, this is the infrared. All these stars are not inside the cloud, they're of course on the other side of the cloud. And these are the ones that will tell information about, very accurate information about the distribution of column density that we can then transform to mass. In this case, we believe that the initial condition of star formation, if you study, I will not spend long here, but this is a core that is about to collapse. We believe what's happening here, this is a smaller core that's been accreted into the main core, and it's tidally elongated. And this will be like the last drop. We think the best model to describe this is a Bonner-Ribert sphere, and this is on the initial conditions to star formation that I tend to study. If you take all the cores in that cloud, and this is why this is important, you suddenly find a very strange result, is that you find the core mass spectrum, so spectrum of masses for those little dense cores, that's very similar to the stellar IMF, is only shifted by a factor of 3. Not a lot of time to discuss this plot, but this is a kind of science that one can do when you have the resolution to study these objects, which we do in the local galaxy. Now, IMF, I don't have to explain to you how important it is for galaxy formation, from galaxy formation to planet formation. Since then, Herschel so the result is verified. There's this shift. The group of Philip Andrea using Herschel finds in essentially all the molecular clouds some sort of similarity and a shift in the peaks between these two functions. Another thing we understood for a while, we thought that the distribution of column density inside the clouds were log normals. We now know we made a gigantic mistake. There's no log normals. All the PDFs of density, of column density of these clouds are actually power laws. We were just being fooled by sampling. Okay, great. Let me now finally introduce you Orion A. So Orion A is the other major stellar star formation laboratory close to Earth. Towards the galactic center, we have Ophiuchus. Towards the anticenter, we have Orion. Orion is strange because it's 20 degrees below the plane. We'll talk more about that later. But it is the closest nursery of massive stars. So there's O stars forming right there. You look at the cloud, it's fairly straight, it looks. You have, the color means temperature, so you have a higher dust temperature here, of course, because of the B stars. And I will now try to convince you that using Gaia and using what we knew about the cloud before, this is a wonderful star former. There's about 4,000 stars, baby stars, YSOs inside this cloud. If we correlate the positions of these YSOs with Gaia, you get a wonderful surprise that there are 2,000 of them in Gaia. Okay, so this was a wonderful surprise because we expected, you know, Gaia is an optical telescope. We'll never see much of what's inside the cloud. But, you know, if you go to 21, you do see actually a lot of stuff. By the way, this is for, I had a wonderful meeting today with Diedrichs and his wonderful group somewhere here. And a lot of people do simulations of galaxy formation. This is a pixel in their simulations, and this is what they call subgrid physics. And this is why we need to study these things locally. There's no way we're going to understand star formation until we understand what's inside the subgrid physics. All right, so here's the result from Orion A. Let me just show you a bit of Orion A. This is Orion A from Herschel. Contours mean, the grayscale means column density, highly structured. And this red stars are the YSOs that are in Gaia. So these are sources that have disks, they have infrared excess, and still they show up in Gaia. So if you just plot, the simple thing you can do is just plot the distance. So you take all the sources in the cloud, plot the distance versus longitude, and you already see there's something funny towards the tail. You know, the tail is further away than the head. And the head seems fairly flat. A better way to show this is just show you then imagine a cut through the cloud. We got -20. So imagine a plane that from the observer to the cloud, and just plot all your data there. And what you get once you do the averages is this. And this is totally surprising. The tail is further away than the head by almost 50, 70 parsecs, and the head is bent. Now, you would never guess that looking at the image, right? And we know of this cloud from the 70s when CO was discovered. We know there's all kinds of gradients across the cloud. But finally, we have a chance to use PPP to figure out what this strange velocity gradients were meaning and understanding what is this cloud doing. Why does it have the shape it has? And why is it forming 10 times more stars at the head than at the tail? This was part, actually, what drove us to study this cloud. Now, the cloud is, again, seeing almost pointing at the observer. There's basically the size of the cloud essentially is twice as larger as we thought it was. And the better way to project this is actually to use Cartesian x, y, z. Quickly from the rest of the talk, x, y, z is x, y. You're looking down on the plane. Galactic center is x, that way. Direction of rotation of the galaxy is this way, and z is a vertical distance. So if you look down on Orion A, from the top of the disk, it looks like, here we go, a very strange bent head and the tail. If you look then on the side, and now we look in galactic center and Z, it's a comet-shaped cloud. It's pointing towards the plane. This was very strange because it was already very strange that the cloud like Orion is 150 parsecs below the plane. We've been telling ourselves the story that maybe Orion was formed by a high-velocity cloud crashing on the plane of the Milky Way. And this was Franco in the '86, and not much work has been done since then, but there's something strange about Orion. And it gets stranger as we go on. Why so far off the plane? Now, you have Gaia, you have velocities, and you have a lot of velocities also in apogee. If you put the two together, you start having a kinematical view of what the giant molecular cloud looks like. And we're doing that for the first time. The first thing you notice is the head is indeed has a different velocity. It's perturbed. Remember the head, the strange head? It's bent, but you know, it has a higher velocity too, which consistent with, well, it suffered something. There was some external agent that pushed the head back. The head, as you can see, is moving back. This is again x, y, it's the same scale as this one. So the head is moving faster than the rest. The entire cloud is moving away from the observer, but the head is moving faster. Now, it doesn't, if you just go through the numbers quickly, what kind of energy, we know the mass, what kind of energy you need to bend the cloud? It's not that much. A supernova would do it. A supernova that explained a million or 2 million years ago would be enough to bend the head of the cloud. Okay, so but now you have velocities, you have positions. Can we use this? Because what's really cool is, I just showed you stars, I never showed you the cloud, because we don't know what is the proper motion of the cloud. But can we say, if we trace the YSOs, maybe we're tracing the bulk of the gas? One more result, to make it even more strange. The vertical velocity of Orion, so the W component, is 0. Okay, so not only is way off the plane, he has a 0 velocity, vertical velocity. But anyway, we'll go back to my previous question. Yes, you can use the stars as tracers, the young stars as tracers to the motion of the gas. And what I'm showing here is CO in gray, is the YSOs I've been using in gray. By the way, not me, this is all work from my student Joao Groschedi. The orange, the pink ones are the YSOs, radial velocities. And here was the first time I realized it's so much easier to get the radial velocity to a cloud than to a star. Radio astronomy works. And if you average in beams, you see that the difference between the gas and the stars is essentially none. So their stars have the memory of the gas. They have a higher scatter. Most of it is because of higher errors. Okay, great. So because means now we can use this to actually figure out what Orion cloud is doing. We have velocities, we have positions. All it needs is a galactic model, and we can go back in time and forward. Okay, so first, if you do that, you figure out immediately, so we're using a model of the Milky Way, but you figure out immediately that Orion is at the minimum, because of course the z velocity 0 is of course at the minimum distance from the plane. And I have a better plot than this one. I don't get you. This is probably, it's too stretched. You see that this is kiloparsecs. This is, in reality, something like this. But what I wanted to say here is, if this works, then we can just take the entire Orion association, get all the YSOs we know of, cross-match them with Gaia and Apogee, and try to do the movie. Let's go back in time and let's see what the clouds were doing. How are they evolving? This is fundamental for us to understand, among several things, how the clouds form, where do they come from. So if you do that, now let's just take all the data that I was showing you. Let's add the data we have, not much for Orion B, for 2068 up there. There's a little cometary cloud. There's a tail up there, 1622. And the same thing down here. The Witch Head, Rigel is right here, and it's Witch Head Nebula is reflecting blue light from Rigel, so we know exactly where it is. And since we have now Gaia positions for all of them, we know where they are in 3D. And we know some of them have velocities. We add velocities from the literature. This is the first rough attempt to figure out what exactly the entire association of the large-scale star formation is doing. And then we do that, and let me just show you, this is what it looks like from Earth. So this is Orion A, Orion B, and the comets. Orion A, Orion B, and the comets. There's the comets on top. What we could do now is go back 4 million years, and you see that they were closer together. This is Orion A. Look, it's not bent anymore. It's kind of straight. This is the comets. And you'll now see in the movie what the comets are doing from 4 million years in the past to 10 million years in the future. And this is what's happening. The comets are being blown off. This one is coming towards us. The head is being twisted back. In fact, I don't have the full movie here. You can talk to me later. We could spend a lot of time here. But what's happening is that the entire cloud has been pushed back. So the head is now being pushed back, but so is Orion B being pushed back. the comets are being blown away from the plane of where they were 4 million years ago, and telling you that, of course, the gas is reacting again to something, and that something, of course, is star formation that must have happened in the last 10 million years, 15 million years. So again, you have the first dynamical picture of gas in 3D, PPP, reacting to what probably was a massive star-forming event, and we know that because we know where the B stars are and all the Blau association. That's it's certainly what caused this guy to be moving up, down, sorry, towards us, down, down, and the entire clouds moving back. So this is also to introduce you to a new survey. We're doing this ESO public survey called Visions. It's been done by us in Vienna, and data release 2 is coming. And essentially all you do, we observe all the nearby molecular clouds that we can observe from Chile every 6 months. And we do that because we want to track the proper motions of all these YSOs. So all these YSOs that are invisible or visible to Gaia are now tracked for the last 3 years, every 6 months. And we're going to do that. We get all the data we can find in the archive. There's VHS, was the previous survey, all sky, that's at least 1 point, the baseline of 10 years. But most of these regions have been observed for a long time, for at least the last decade. We plan to use all of that, and of course doing all the kind of bread and butter science we need to do in star formation, IMF, the disks and all that. We are very interested in measuring now precise motions of YSOs, because those will tell you again that they'll track the motion of the gas, and we probably can even see there's any motion inside the cloud, and then is this how clusters form. Someone has some ideas on how clusters form, and then one of them is that you have some kind of conveyor belt and stuff will fall to the middle of a potential well. We can test that now. Not now, in the couple of months. DR2 scheduled for mid-2020. Here are all the clouds that we go every 6 months and observe. So it's a major work, but we are very excited because this is the number we're really hoping for, that we're going to be able to do 1 milliarc second per year precision on the measuring of all these YSOs. Of course, then we have Gaia. We'll tie them to Gaia. So we no problem about distances. The cloud is not that extended. So we'll have the full picture of not only the very low column densities, but the very high column densities that are forming the stars. In the summary, by 2020, Vision will replace 2 masks for all the nearby regions from the south. If Calar Alto has that detector that you mentioned, then we'll do it from the north too. And it will deliver proper motions for sources that are invisible to Gaia. That's great, that's for the future, but can we do something now with Gaia? And yes, we can. For that, I need to introduce you to the Gould Belt. The Gould Belt is this disk of gas, and first it was this of bright stars that was identified by Gould, Jeremy Gould, actually by John Herschel before him, but he didn't make a big deal about it. And Jeremy Gould was a Harvard, I think was the first PhD in astronomy in the US. He was a PhD with Gauss in Göttingen, and he brought all these new ideas on how to develop astronomy to the US. And then he went and was director of the observatory in Argentina. And he was mesmerized by the fact that there's this disk, this ring, and he's complaining that John Herschel does not appear to have recognized the fact that this zone of bright stars may be traced through the entire circuit of the heavens, forming a great circle as well defined as the galaxy itself. There's a galaxy and there's this wonderful ring, and the ring is inclined by about 20 degrees. I'll show you here. This is the galactic center, and this point connects with this point. So you imagine you have a plane of the galaxy and you have a ring about 20 degrees. If you want to look at it at night, you can even see it. There's this is kind of part of the ring. This is the galactic center once again. Now you know the pipe, you know Fucus, and these are the SCO stars, and those are the Gould Belt. And turns out when we discovered that there's clouds and CO and molecular star formation. Remember, there was no star formation in 1874. In fact, there was no star formation until the 50s when people realized that they have to be forming in these clouds. this picture emerged, and the picture is the sun is inside this local structure, which is this ring, and it has cosan on one side, Orion on the other side, and all these regions of star formation. So of course, they're massive stars. Now we know, well, there's all this gas, and this ring is supposedly expanding. So not only is the ring inclined 20% by 20 degrees, it's also expanding. And then Hipparchus provided a gigantic boost to this picture. Okay, so you can see it in B stars. So these B stars, this is one of paper, the distribution of B stars, X, Y, same thing, Cartesian coordinates, you'll see it here. Here is your 20-degree plane. And another picture from Hipparchus, and this was a very solid representation at the time of what the Gould Belt was. Several models have been described since the 50s, from the free expansion of an OB association to a rotating disk, expanding shells, the high velocity cloud impact that we talked about, and even dark matter clump impact. So there's a lot of models for this peculiar structure on which the sun seems to be in the middle. Now, and I have to say, even with Gaia DR2, this is Zib et al., here's the latest on the Gould Belt. The sun is somewhere there. It's less, the shape changes a little bit. You get cosan, Orion. It kind of expands, not perfect, but you see kind of seems to expand. And if you see it from the side, it looks like this. From the other side, it looks like that. So how do you get distance to nearby clouds of Gaia? So this is now the idea. We have positions and distances to 1.7 billion stars. We should be able to do better than before, and this is what we try to do. How do you get a distance to the star? Well, the simplest way of doing it is to just, if you know the extinction and the distance to all these stars. You see there's like blue stars, there's red stars there. Obviously the red stars must be on the other side of the cloud. And all you have to do then is do a version of Max Wolf diagram, Max Wolf from Heidelberg, and where you'll have on one x distance, the other one extinction. So this is, this will be a nearby star, no extinction, no extinction, no extinction, and suddenly extinction, and suddenly everybody has extinction, so you basically hit the wall. And this is the simple method we're going to use. To do that, you need, of course, to get the distances and the extinctions. The distance you'll get from Gaia, as you'll see, and the extinctions you'll get from a method I'll show you in a second. But let's just show you the pointings we used on the entire sky. We basically went to a catalog and show us all the nearby star-forming regions to within 2 kiloparsecs. And let's do the same thing. Let's derive the distance to all these points, to all these beams towards the clouds. But not only towards the clouds, but towards regions where no one looks, the region between the clouds. And when you do that, here's the method to infer the distance. And this is work done by the group of Finkbeiner, Schlafly, and Greg are here. So you're before Gaia, this is the posteriors of extinction and distance. You see all these bimodal distributions. It's not there's some degeneracies. Once you have Gaia to this plot, this happens. So a lot of the degeneracies are gone, and your measurements become much better. So then you have to do is, what I just showed you, the model is simply this one. You just measured all towards one line of sight. You measure the extinction to the stars, you plot them versus distance, and that's the wall. So no extinction, then suddenly a wall of extinction. Then all the game is about how do you define this line, and this is done by Greg and by Schlafly and by Finkbeiner using Bayesian framework. And this is before Gaia. Look what happens to the uncertainty. Of course, the width of this distribution is the uncertainty to the face of the wall, so your distance measurement. Once you have Gaia, your uncertainties collapse. And this is amazing, because we've been talking about distance to clouds for 150 years, and we were up to errors of about 30%. And with this method, suddenly, we are talking about uncertainties of 5%. And when that happens in any field of astronomy, magic, you're always bound to find something. Let me just show you how much of a feat this is. This is Mazur's distances. So these are Mazur's distance using VLBI measurements. Very time-consuming. People spend careers doing these measurements here. And then if you have the dust measurements from this method that I just showed you, all you need is a couple of hours and you have all your measurements. Now, the comparison between the two is excellent. So they agree within 10%. There's no really systematic offset. And the gigantic advantage is that you don't need a maser. You can point anywhere in the sky and you get a distance to a cloud. Here, of course, you need a maser. You need to know where they are, and you need to track them for a long time until you get their orbital solution and the astrometry data from it. So this is the revolution. What I'll show you now is just one simple outcome of this revolution. Let's go back to what we were trying to do. Let's get the distance from this jungle. What's in front of what? We don't know. We have, surely Taurus is nearby, but you never understand Perseus. There's, depending on papers, papers you read, you get 300, 250, whatever, 220. Orion has been complicated too. You easily find 500 or 350, or, you know, there's these long, large uncertainties on a lot of these clouds. What happens now, if you take all of these measurements, so you have x, y, z for them, so you have L and B and the distance, then you convert to x, y, z. Let's put them on the xy plot. And when you do that, this happens. Again, galactic center that way, sun in the middle, and all the nearby star-forming regions, or the large majority of the nearby star-forming regions, form this incredibly narrow structure, 3 kiloparsecs long. 3 million solar masses. And we've been very, very close to it for a long time. Now, if you look from here, and you look along it, it's not exactly straight, but you find this. You find that it's actually up and down the plane. So it's like a plane. It's not exactly just a line. But the way to do it, of course, you look it from this side and see what the plane looks like. And it looks like that. It's a wave. And it's a damped wave. So there's the sun there, you have Corona Australis on the plane, it goes down to about 200 parsecs, it zips by the sun and goes up to Cepheus, Taurus, Orion, and go down again, and then up, and then kind of we lose the ability to do the measurements at around Cygnus X. So from Cygnus X to CMA, there's only one structure that includes all these giant molecular clouds that we've been studying forever, and giving you a completely different perspective on things. So we've been thinking that these were much more randomly distributed, but no, they're highly correlated. In fact, most of the stuff in nearby is nothing. There's not a lot of dense gas in between this structure. So this was just one of the first discoveries, which is simply, as I was saying before, if you have an uncertainty that goes from 30% to 5%, you're bound to find things like this. We call it a Radcliffe wave because of all the support I got for last year while I was working on this, but also because of the wonderful work that Radcliffe has done in supporting women in science, and particularly you have to go back to Henrietta Leavitt and Cecilia Payne. They were all Radcliffe graduates, and I think it was very fitting to call this the Radcliffe wave. Here's are some physical properties of the Radcliffe wave. The length, 2.7 kiloparsecs, 60 parsecs scatter, from across the wave. Amplitude 160, and the mass more than or about 3 million solar masses. Yeah, don't take pictures because this is now accepted, and All right, so a quick demo of the Radcliffe wave. So I lost the high resolution again. Let me try to. This will not last long, but let's do this quickly. Oops. Here's the Radcliffe wave in 3D. Let me first show you where the Gould Belt is, or where we thought the Gould Belt was. So the Gould Belt, this is a 3D image, but I have to say that this is a resolution problem that with a projector, and essentially the Gould Belt is empty. There's nothing inside the Gould Belt except the points that we have arbitrarily chosen to define it, which is Cosan and Orion. There's nothing here, there's nothing there. And even what we thought was the other side of the ring, it doesn't really fit a ring. The other way of looking at it is if you look end on, and you see that you have essentially an empty ring. But we can go there, and now we'll just zoom in. And you see that there's Taurus, there's Perseus, they're really not fitting anything. So the first result is there's really no such thing as a Gould Belt. This is a 150-year structure that it does not exist, which is very, very strange. Should I do this again? Oops. If only it could stay at that resolution, that'd be great. Another one is the local arm. Let's forget about that. So maybe this is a local arm, and let's just concentrate now on this. Maybe this is just, structure is just what we used to call the local arm, or the Orion spur, or the CMA, or the Cygnus arm, the CMA Cygnus arm. But it's not clear. This is the best description of the local arm. This is done by Mark Reed. These are masers. And you can see, you suddenly see that the advantage of not having to deal with masers but choosing your own line of sight, you get much more statistics, and it's clearly not a good fit. And the reason is first because you're doing a log spiral fit, and they have a lot of points somewhere here, and they totally miss Cygnus X. So it's perhaps the most dominant part of the local arm locally. I will then go, I think, I'm not playing with the resolution anymore, and moving on a little further. The first question one asks is, how can it be so straight? And second, how did radio astronomers miss it? They know of this since the 70s, discovery of CO in 1970. How is it not obvious for radio astronomers? So here's color-coded, coded by velocity. Essentially, you have CMA, Orion. The wave goes something like this. And of course, these are further away on the plane, and that's why they're not part of the wave. The reason is that it's actually not such an obvious thing to find. This is a PV diagram from the same plot, and the wave is essentially the straight line here that you see here. And in a sense that that's what you expect from bulk motion, right? So if you have a train arriving at the station, you'd expect it to do on the PV diagram, velocity position, some kind of a slope. What we've done here is said, well, let's do a bit of reverse engineering. If we know the positions and we know the velocities, we know the galactic rotation curve, just put them on these measurements on where they should be, apply a rotation curve, and predict what velocity they should have. And this is what they should have, is the red points, which do not fit the data. So this thing is not just pure rotation. This is a thing, is a coherent structure that's doing a bulk motion around the Milky Way. And it was not obvious because the signal, I mean, you would never be bold enough to say that you will use this to prove that there is such a structure. So the Gould Belt is gone. We've talked about that. Let's go back to this obvious case for the Gould Belt. These are the B star distributions from Hipparchus. And then you start saying, why were you confused or fooled by it? What you do see instead is these two lanes, which is very interesting because this is exactly where the Radcliffe wave goes through. Orion is somewhere here, and these are all the B stars that are part of the Radcliffe wave. Young stars formed in the wave, and these are all the young stars formed in the Cosan association that is not part of the wave. That's one. Oh, yeah, but there's another one. What about the expanding? I just showed you. Last year, we have this paper that proves to you clearly that the whole thing is expanding. It's not. What's expanding is, or moving, is that they have two large-scale structures, the Radcliffe wave and the structure that includes Cosan, and they're just moving away from each other. And you're sitting in the middle of it and seeing these things going away, and assuming, of course, that in projection you're inside a ring that's expanding. So I think I convinced you, I hope I convinced you that there's no such thing as the Gould Belt. And instead, we have this new picture of the local neighborhood, which starts somewhere in CMA over there, and then goes down to Monar 2, and then Orion here, then jumps on to Perseus, and Taurus, and goes up to Cepheus, down to Cygnus and Cygnus X over there. And which is not part of the structure that where Scosan or Ophiuchus is. This is another structure that, if you calculate the distance, does something like that. Okay, so this is the new local neighborhood. There's no such thing as a ring. What you have is the sun sitting to this massive filament, and make you think what exactly is causing this filament. I will wrap up very soon, but I spent a lot of time looking at equivalents of what this structure is in nearby galaxies. And maybe it's a spur. I'm now convinced that it's not a spur. It's more massive than a spur, until I come across Mark's Reed's favorite Milky Way analog, which is this galaxy here. And you see a spiral, you see a bar. What you notice too is that your spiral is made of segments. See the segments here, there, there, and there. So perhaps what we're looking at, and we've been living very close to, is one of these segments. And it's more massive than we thought it was. And this is perhaps what the Radcliffe wave is. There is one RV anomaly that I need to, this will be the last result. This is from Schlafly, measuring the dust properties with apogee of all the nearby lines of sight to the sun. And he finds this very strange pattern, blue, red, which is totally unexplained. If you put on this the Radcliffe wave, you'll get that. So I think what's happening here is that the dust properties of the Radcliffe wave are different from the rest of the Milky Way. In fact, they're very comparable to the ones in the SMC, suggesting that perhaps the metallicity of the Radcliffe wave is lower than local. So this is very exciting. This is something that has to be redone. We have now more data to do this better. But I find that angle very, very striking, and as it aligns with the Radcliffe wave. Finally, let's leave Radcliffe Yard in lovely Harvard Square and go to visit the Radcliffe wave. This is done with a worldwide telescope. Those are the planets. This could be done with Gaia Sky, by the way. But it was done with a worldwide telescope. And then you have the nearby stars converging, and suddenly you have the view of the Milky Way. And what we think we're looking at is, this is of course a cartoon, but these are the distribution of the measurements that we have. And as you'll see, they go below the plane and above the plane, as will be more obvious as we zoom in. The galactic bar is up to scale. Everything is up to scale here except that it's a cartoon. And then you'll see the sun very, very close to it. So I want to end with just one note, is that because we know the motion of the Radcliffe wave or stars in a Radcliffe wave, this is very preliminary. We know the motion of the sun. We can now go back in time and ask when did, or what is the relative velocity between the sun and the Radcliffe wave? And you soon find out that the sun crossed the Radcliffe wave 13 million years ago. In fact, it crossed it at Orion. So we're just coming from Orion. Orion 13 million years ago was full of star formation. All the B stars that you see in Orion, all the association is about 15, 20 million years. These were all stars that were forming at the moment. They were exploding as supernovae. And And I think it will be, as mass spectrometers get better and better, it will be a wonderful line of research. As you probably know, but we're finding iron-60 everywhere now in Antarctica, and we cannot find a reason for that except from supernovae. There's lots more here, but I would like to just stop here and leave you 3 simple results. That the Radcliffe wave is the new paradigm for the local neighborhood. No more Gould Belt. It in itself is a new context to understand cloud formation and star formation and galactic structure. To take the connection between, I just told you about maybe the Radcliffe wave as a different material than from the star formation in Ophiuchus. This has to all to be developed. But once you have this very large picture connecting everything, suddenly everything looks more interesting. And that the Earth, this touches us. The Earth just crossed the Radcliffe wave. It will cross again in 13 million years, by the way, because of the radial motion of the two. By then, probably not so, it will cross it in Cepheus. Not a lot of star formation in Cepheus in 13 million years. But we just came from a hotspot. In fact, we are still in a hotspot. And that's no surprise that we find all these disks around Beta Peak, and we're crossing this 40 million-year-old, which are great for ALMA, so you get these wonderful images. But this is where we are in the galaxy at the moment. And I'll stop here. Thank you.
Thank you so much for a truly wonderful talk, very thought-provoking, and I have no doubt that I'm not the only one with like a long list of questions. So, floor is open for discussion. Yeah, Andreas.
So very nice talk and overview to learn about all the star formation regions. Yeah. So I'm wondering about the connection, calculating back to the solar positions 30 million years ago. I mean, is it just by chance, or is there any meaning that at the time 30 million years ago the star formation happened at the same time in Orion?
In Orion, you mean?
Yes.
No, I think it's
just by chance.
It's pure chance. If you look at so now I'm trying, if you track the masers, you trace back the masers, you track past the sun, and they're basically doing this over time. So we just passed it when it was forming Orion. When we'll cross it again, we'll cross the young stars that were born in Cepheus, but they will be nothing as exciting as crossing Orion, which was 13 million years ago.
And the position of the local bubble is consistent with that?
Yeah, so the local bubble, I didn't brought it in, it'll be a whole new talk. I think it's consistent with the fact that we're now, so we crossed the Radcliffe wave. We're now, in the last 2 million years, we crossed Scosan. We were very close to Scosan. Oh, Scosan crossed us, it doesn't matter. We just passed very close to LCC, one of the clusters. And about 10 supernovae have been going on since the formation of Scosan, and there is now evidence on the surface of the oceans that points for this iron-60 peak that you can put a time to it, which is 2 million years. If you do the same thing, there will be a different talk. You'll see that the sun was very close to LCC in Scosan. Those blue stars I showed you that form the Gould Belt, we were very close to them 2 million years ago, and it must have been one of those that exploded, and it has this nice 2 million year iron-60 on the oceans. And there's another signal at 8 million years, and again, consistent with the idea that we're not in some quiet spot of the galaxy. This is actually a dangerously and exciting place to be in the galaxy.
Thanks for the nice talk, Joao. So can you speculate a little bit about what is keeping together the Radcliffe wave? Because if there's supernova in the solar neighborhood, there's the Orion A superbubble and some other supernova events. What is keeping together this structure?
This structure? What is it keeping together? Well, then you go to the origin of the structure, which is, why do we have the structure at all in the beginning? There's several models. I mean, the fact that it is metal poor compared to the rest of the local neighborhood suggests that it's probably not from around here, and it will be, you ask me to speculate. It could be this picture where, I forgot the name of someone in Didrik's group that works on this band. I think band, yes, there is. You have gas that is in the halo and rains down on the, every so often, rains down on the disk of the galaxy. And it rains down, it gets tidally stretched and forms these long filaments. This is, of course, this is not certain. Some people say that will never happen. That's one way you get it, and it's then you get the entire structure coming together, and that's what kept it together. It was formed together. Another one is a simple galaxy, spiral arm. You have, I don't know how to explain then the wave, but you can, this is what maybe how you, if you look at the size of the structure, you do not find it possible to be caused by feedback. It's too big. Feedback is 500 parsecs on average. This thing is 3 kiloparsecs. So it must have been the galaxy, some gravitational instability, some spiral arm process that you accumulate the gas. You must have accumulated the gas at the same time, because the entire thing is star forming. There's no age gradient. There's regions about 10 to 20 to 30 million years, so stars are already out. But the entire structure is star forming. So it's suggesting that it has to be put together in one go. And this calls for galactic structure scale processes. So what keeps it together? It was formed together, and now it's dissolving together.
Further questions? As I'm walking down, especially people high up are invited to ask questions so that I don't have to run up again. All right. Okay, I'll start by asking a question myself at this point. So I'm mesmerized by just the total wonder about what we now know based on Gaia and what you're showing here. I want to ask an Occam's razor question.
Sure.
So you showed that it doesn't quite match the local arm.
No.
And you showed that it doesn't quite match the rotation curve.
Yeah, but for the local arm, let me just say, we don't know what the local arm is.
Okay, so that's where my question is going, because I think for both of these, I wonder if the uncertainties actually justify making that statement.
Yeah.
Because for the local arm, it's obvious indeed. It depends on the inclusion of your Mesa sample, on your selection function, whether or not you would call this consistent with the local arm. But then also for the rotation curve, it seems to me that, do we really know the rotation curve that well that we can say on the level of a difference of, say, a few kilometers per second, that it's actually not consistent,
10
right?
kilometers. You get to 10.
Yeah, there was a 5 kilometer per second offset
No,
or so.
it's a curve. So you have there, at the maximum, you have about 10.
If you want, right? You're the guest. Okay, fine. We have 10 kilometers per second. Well, my question is do we really know the rotation curve at the position of the sun at that level? Because there are systematic differences in terms of the local orbital circular velocity that are actually in excess of 10 kilometers per second. And it means that you can pick your favorite model and maybe move this a little bit relative to where we actually see the observations, right? Because the red here is a prediction based on whatever rotation curve you adopt.
Right.
So could you make it consistent? What would you need to do to make it consistent?
Good question. No, that's a good point. We should try that. I don't think you'll always get the curve because you're going radially.
Yeah.
It's just a matter of how far off you are from the straight line. And the argument, I would say, is that this is a straight line. Most of it falls along the slope. I don't. But it's a good point that we should try. I don't think. What does it has to be for the red points to match the line? Good point. I don't know. I suspect it will be unreasonable, but I don't know.
Wait.
Sorry.
At the anti-center position, you should have 0 for the rotation curve by definition. So therefore, this offset at 180 degrees is obvious, yeah, that something is different to the rotation curve.
Right. And it doesn't. Yeah. Because we know that the whole thing is moving. So if you UVW, the whole thing, Orion, because we know very well Orion, U is -10, and it's consistent with the whole thing moving -10 away from the galactic center. V and W are 0. And which makes the scenario of an external accretion complicated, because it means that as you accrete, you immediately get the right velocity, which probably it could be, but you kind of have to expect your accretion to come and immediately get the velocity of your rotation velocity of your disk, which is maybe asking for too much.
So this was identified in the dust and the young stars. Is there any, I mean, this is close enough, you should have a lot of stellar constraints from Gaia on older stars. Is there any other older stellar population or stellar overdensity associated with this feature?
This is what we're looking for right now. So one question you might ask is this a material wave moving through, or is this just oscillations? And the hint from Orion that is at the trough of the wave, so the wave's at the bottom, there we have a lot of measurements. It's at 0. It kind of suggests that the whole thing is oscillating. It's not a moving way, but what we're doing now, and we expect DR3 and DR3, in particular DR3, because you will have your velocities will increase the number of stars for which we have radial velocities. We have to identify these populations. And most of them are not known. There are 20 million years. As you cross the plane, your ignorance goes exponential because it's so confusing that all the population. Now Gaia will help solve this, but before Gaia, no one dares working on nearby populations against the disk because it's very, very hard. You get confused. So Gaia will completely change this, and this is what the DR2 will do for us, I think. We'll have a kinematics of the populations, the young populations associated with the wave. We could tell between different wave models.
So what was the width of the arm again, of the Radcliffe wave again? Yeah.
1 sigma 60 parsecs.
60 parsecs, okay. Then gives it a gas surface density of 20 solar masses per square parsec, approximately. If you take the 3 times 10 to the 6 solar masses and you stretch it over the full 3 kiloparsec and that width, it's about 20 solar masses per square parsec. It's a little bit low for a spiral arm, but it seems to be sort of in the right ballpark, at least, order of magnitude.
It is.
So,
yeah, it is a bit low. Let me just say, the way we do it, we just integrate. It's very hard because you never know, there's no 3D plunk. So you have to make all kinds of assumptions. We subtract backgrounds all the time. The numbers could be off by a little bit, but you compare it to normal, to other, like M51, this are on the lower side of the mass. You're right.
Yeah, but M51 by and large, it's just much higher pressure. So
thing,
yeah. Okay. Yep.
Very small thing. In one of your slides, you got the numbering of the Gaia data releases wrong.
Oh,
you might consider to correct that.
Sorry.
That's the risk of giving a talk to a room full of Gaia people.
EDR3 next year, DR3 2021. Sorry, forget my slides.
The one for last year is
I think there is confusion. There was a slide of visions where there was DR1, DR2, and DR3. And it confused me too at first because I saw DR2 next year and I thought, wait, didn't
Visions
Gaia?
DR2 and Visions DR1. Those are not Gaia. Visions is this survey we're doing in infrared of all the nearby clouds. And I mentioned DR1, DR2, but I should have said Visions DR1, Visions DR2. Sorry.
All right. Good. Yes. All right.
Hi, I was wondering, you already hinted a bit at it when you talked about the age gradient that is not there, but is there any systematics in the ages of the star-forming regions and the locations where they are in the structure?
Along the wave, you mean?
Yes.
That's an excellent question because we haven't looked. So there's these chunks. I cannot go back to the 3D, or maybe I can, because it takes. Okay, maybe I can. There's a big chunk missing here. Okay, and this is perhaps Blau's Kastau, the famous Kastau that for him was the origin of the Gould Belt. It's maybe what we need to find. So, or maybe Alpha Per, but Alpha Per is a cluster, young cluster. It fits right in the middle. It's just that it has the wrong velocity. It's just passing by. So Alpha Per doesn't fit either. But there's all these populations that we need to look for, and this is the big event that I showed you, where you see the clouds being, expanding. Something happened here, and more than one thing, because Perseus is also very perturbed. As is Taurus. Taurus is actually not perfectly aligned along the wave. This is Taurus. And I believe this is just gas that has been pushed back from the event, and you have all kinds of, but this is for another talk. So there must be older populations, and this is a search that has to be done because you'll have a lifetime for the wave. It's just that we don't look at them normally. No one looks in the middle of nowhere looking for 20 million year old stars. And this is why Gaia DR2 is going to be just what we need.
In your picture of the Radcliffe wave, you had some blue points.
Yes.
Some of which were spatially very close to the red ones.
Yes.
What's the difference?
Is the fitting. So the fitting, the way that the way we do it, to be fair, we took all the regions, and then we allowed a statistician to go find correlations inside the data. And the only significant one they find is this one, the Radcliffe wave. And this is without the tenuous stuff. The tenuous stuff comes after. In fact, the stuff between the major regions, we went back and tried to see, I mean, if are they part of this? Because of course you're looking at the 2D, you have no clue, and they all align perfectly on it. So the first selection is done on the entire sample of GMCs within 2 kiloparsecs, and it's done blindly. So we're not forcing it to find a wave. This is done by Josh Spiegel, who's an astrostatistician.
Some of the points are very close to the ones.
Some of them are very, very close, and it's now a matter of sampling. So, for example, SCOSAN, so what we thought is part of the Gould Belt, is very, very close to the, we have this, do I have it? No, they were here basically. And they were, they move totally different way, they have a different, they're not part of this structure. Another thing you might have seen is that it looks like there's other alignments, and when you look into and this is a recommendation for all of you that work in 3D, work in 3D. You'll find that what looks to be aligning in 2D is very rarely aligning in 3D. So when you travel the data and you navigate the data in 3D, you find that some of these correlations that you see in one of the projections, remember the Gould Belt example from Hipparchus that looked like a wonderful disk. Once you start navigating it in 3D, you realize, well, it's two lanes, and now we know why. Well, one is the Radcliffe wave, the other one is the SCOSAN. Yeah. So I have to say though, there are probably more correlations in the data, so more structures that are connected, but those we're not yet on them.
Any final questions before we close today's colloquium? Okay, and then before we thank Joao again for a truly wonderful talk, I would like to announce next week's colloquium, which will be by Paola Pania from MPIA on a further zoomed-in version of what is happening in the local neighborhood, namely planet formation within protoplanetary disks. So I look forward to seeing you all again then.
Yeah, by the way, all those disks, they're all part of the local
Yes.
part. So they're all part of this story. And that's why we have these wonderful images of them. Sorry.
Yeah, I agree. Thank you. So before we thank Joao again, we are going for dinner with Joao this evening at 6:30, although the restaurant didn't pick up, so please check with me if you would like to join. Tell me and I'll adjust the reservation for the total number of people. We're going to Salerno, which is here around the corner on Brückenstrasse, 6:30, thereabout. And with that, let us thank Joao again. And,
Thank you.